Hi everyone, welcome back to physics class. And today we will be discussing and going over essentially the speed, the distance, displacement, and acceleration with another problem, just so that things can be clear before we start moving on to actual uh, relation or speed and distance and acceleration, or sorry, not speed, but velocity, acceleration, and displacement, those relation developments, which are really important. They're called the equations of motion. I really wanted to go through another example so we can be clear about these basic concepts and how they're being used. Um, and as always, there's going to be an in presentation um, example or a question that you'll need to answer with an end of um, video lecture assignment that you will need to complete and submit to me before 5 p.m. Today. So, just to start with things, let's go over what we've done before. The first thing that we had discussed at the start of this unit was the distance versus displacement argument. Now, distance is to do with the measurement of space between 2 points, and then the displacement has to do with the shortest numeric measurement of space between 2 points. Now, the important distinction between these two is that although they're numeric measurements, distance is a scalar quantity, and so it's only got a magnitude rather than direction, whereas displacement has got both a magnitude and a direction as well. That's why it's a vector quantity, and that's the main difference between a scalar and a vector quantity. Moving on, we've done the frames of reference example, which was the displacement between uh, the University of Dayton and CJ, which if you're moving from University of Dayton right here to CJ, this is kind of northwest. So that's your direction, and this is the displacement. The image was taken from Google Earth. What we talked about is the frame of reference, and what I hadn't realized is that some of you had trouble estimating this when I'd asked you to complete or find the location of your computer in your room during the distance learning practice days, um, what that location might have been and what that displacement was. So one thing I'd said that based on the frame of reference, which is your x-axis and y-axis, you can locate both the University of Dayton or CJ um, from where you stand. Now, the way you do it is for these displacements, you go around the x-axis, note down this location, and go up the y-axis and note down this coordinate, and that's your location for University of Dayton. Now, using based on that coordinate for x and y, then you can use Pythagoras theorem to find what this displacement is. Now, it assumed that you already knew that. So for those who did not or had forgotten, I just wanted to do a quick recap of what Pythagoras theorem is. So, and then the overall displacement does not change. And once we get to two-dimensional kinematics, I will actually go into how you actually find this displacement because this is not a right angle triangle at this point. And it's all Pythagoras theorem has got to do with right angle triangles, and it's the vector addition then happens with based on right angle triangles as well. So Pythagoras theorem essentially is if you've got a right angle triangle, so one angle is 90 degrees, you can use the base and the perpendicular to find out the hypotenuse, or the base and the opposite to find the hypotenuse in this case, which is basically uh, the square of the base and the perpendicular is equal to the square of the hypotenuse, right? And that's your trigonometric as well, where you get all those trigonometric functions. But that's one thing I wanted to go over, and that's what you had to utilize in that location or displacement of your computer from three different corners uh, during one of the distance learning days that you had to submit, um, or after lecture assignments. So that thing. Next, we covered velocity. Now, velocity again there are two terms that we usually use interchangeably, but speed is a scalar quantity, And it's simply distance divided by the total time taken to travel that total distance. Whereas displacement or velocity is the total displacement divided by the time taken to cover that displacement. And it's simply given by this formula where you're just subtracting the initial position from your final position and the total time taken for that. Um, for velocity from the different plots, we've gone over this where for the runner example. Um, I'm not going to go over this again. And then there was essentially the acceleration part. So acceleration is simply the rate of change of velocity over the period during which that velocity change occurred. And this is the formula that is used to calculate the acceleration for any instantaneous change, or not instantaneous, but a change over a given period. Right, so today we're going to be applying these to a newer example, but since it's still displacement, velocity, and acceleration, and speed and distance included, of course, um, it's going to be within the same focus area, but it's just a different route that we're taking. So what I did was, for this particular um, case, is I mapped out a journey from CJ to the Sisters of Notre Dame um, campus over in Cincinnati. What I did was I took a different route this time. It's a total distance of about 50.7 miles, and it will take about 1 hour to complete. Now the route directions are based on Google Maps. That I'm traveling on Ice Edwin Moses Boulevard for a distance of 2.5 miles for 5 minutes. Then I'm traveling on I-75 South for 14.6 miles for 13 minutes. Then I-71 South for 16.2 miles for 23 minutes. Then I'm continuing on 71 South for another 17.1 miles for 16 minutes. And then I finally uh, turn on to Columbia Avenue for drive on it for zero point 0.5 miles for another minute to finally reach the campus of Sisters of Notre Dame for a total distance of 50.9 miles, which took about 58 minutes based on this little breakdown that Google provides. Uh, so once you do this, what can you actually do with this data? Um, so one thing I could do is I can actually plot it. So this is simply the distance that you saw in the previous slide, plotted against the time. Does this seem correct? Well, let's think about it here. So the time is increasing. So it's increasing from 0.08, 0.022, it goes to 0.038. That should be hours and not minutes. So that's my mistake. But the distance should be increasing, which is happening. Now the distance does increase, but the time has reduced. So again, once again, this should be saying hours rather than minutes. The time is decreased, so this doesn't make sense. This chart is not correct. What you can do instead is you can start adding the time. So the time that you saw in this slide, you can start adding this time over. So you've got first 5 minutes, and 5 plus 13 would be 18 minutes. 18 plus 23 would be 30 and 48, 41 minutes, and that sort of thing until you get to 58 minutes. And that distance will be increasing, right? So you'd be adding distance as well. So 2.5 plus 14.6 for the 18-minute mark, and then so on and so forth. So what that looks like then is that this is the total distance in miles that you're covering, and this is how the time is progressing um, as you're covering that distance. So this seems more feasible. Now there's a lot more things that you can do with this information, and that includes um, that you can. Sorry. So what you can do then is, well, there's one thing I forgot to add, and that's one thing that you can do first is that you can start your journey at zero. That's one data point that was missing. So you always have to start from zero. So we start at zero time until we reach about 58 minutes or nearly 1 hour to complete that 51-mile journey or so. So that's one thing you could do. The other thing that you can do based on the same frame of reference example that you can point out what the locations were for a given data set. what you can do with position time plot, which essentially this one is, that you can use the distance versus time. So remember your dimensional analysis, where you can create new units from base units. So this is a base unit of distance or length, and this is time again, and you can create a near unit. So we've got distance and time. So you can essentially create speed from this, or you can measure speed from this. So one way to do it is, if I were to draw these 2 points right here. So if I were to draw these two lines and then measure what the x values were, and then I have to draw these two lines and measure what the y values were on the distance scale, what that provides me with is that at this point it's measuring 42 miles and the time is zero point 0.8 hours, whereas at this point the position is 4 miles and the total time is zero point 0.1 hours approximately. So what I can do then is I can use these values, substitute that into my formula, and I get an average speed of 54.9 miles per hour. Now, what you've done essentially now is you've created a slope, and what you've done is you've measured what the slope is. Using the slope, you can measure or you can come up with an equation which will tell you what the distance would be based on the time that you're using, right? So y is equal to mx plus c. That's one thing that you can do, but it won't be accurate. So remember, you're in the last lecture when we talked about uh, the power of prediction using Excel charts or the spreadsheet charts, where you can actually do a trend line fit for linear or polynomial curve fitting, and that would give you an equation with an r square or a r square statistic, which tells you how accurate it will be able to predict the data. That's what you're trying to do, but this one is a linear fit, and this won't really do a good job here. Um, but what you can do with this information right here is that with using just simple distance and time plot or position time plot, you can calculate what an average velocity is for this leg of the journey, which here is about 54.9 miles per hour. Now, in order to cover the entire journey, if I were to move these points a bit further, so let's say I do my final point, which is about 51 miles and took me about 0.98 hours, and then approximately, because there's no kind of scale around here. And then x was at 0 for the initial point and t was at 0. What I can do again is do that again, draw that slope and measure it again. And now my velocity is coming down to 52.04 miles per hour. Now, if I go back to the original calculations, so now this is my original distance as provided by Google. This is my time in minutes as provided by Google. This is the time converted into hours. And you can simply do that by dividing this value, each of these values by 60, because 1 hour has got about 60 minutes. Not about, but 60 minutes. And then what I've also done is I've corrected the distance. So it's simply adding the distances together. So I've added 2.5 miles and then added 14.6 to 2.5 miles, and I've added that until you get to your 50.9 mile journey as it was stated around here. And the time corrected also is doing that, which you can then use to create the plot that I'd shown you before, which is this one, right? And then the speed can be essentially calculated. For each leg of the journey, you'll have a different speed. Remember, we're not talking about velocity here, we're just talking about speed because we're not considering direction at the moment. But speed is for each of the individual legs of the journey. For the total distance and the total time taken, you can work out what the average speed of your journey was. Now compare this to the original one that, or the one that we calculated. This is pretty close, but again, this is not accounting for this little uh, dip in speed or this little increase in speed that is happening around here. So that's why this one's a bit more of an estimation um, rather than an exact calculation, which is this one. So the next thing that we're talking about is, after you've done all of this, um, the other details that you can actually do is, and then this is using Google Earth now, is that you can map out what the displacement is, right? So this is Google Earth. I pinpointed where CJ is and where the Sisters of Notre Dame Dinamere campus is, and then uh, essentially using the ruler measurement tool within Google Earth, I've measured this is what my displacement is. Now remember, the displacement is still going to take the same amount of time that it took you to cover that total distance, but your displacement is going to be much lower because it's the shortest distance that you can, or shortest space between 2 points. Um, and then using the same kind of scale, what you've got is that the speed was 52.66 miles per hour. But since the total displacement is much lower than the actual distance, my velocity is going to be much smaller than the speed. But note here is with that velocity, which is now 40.1 miles per hour, I've got added direction to it, which is if I'm traveling from CJ to the Sisters of Notre Dame campus, it's going to be about southwest. Given north is pointing up, south is pointing down, we've got west, and then we've got east on this on the right hand side. So that's one thing that you can further add to this information. So now you've covered speed, you've covered velocity, you've covered distance, and now we've also covered displacement. Now, what you can also do based on this little data that I've calculated based on these individual distances and time map in hours. I've calculated these speeds uh, for each leg of the journey. What I can do is I can plot them. Again, if I plot them directly, this does not seem right because this does not mean that I went through and I did from 0 to 30 miles per hour in 0.008 um, of an hour, 0.08 of an hour, right? That does not make sense because if you were to multiply it, and let me get at my calculator, and you're welcome to use your own calculator at this point. If I were to multiply it with the total distance that I've covered in this case, it would come out to be, so remember again, this is a triangle, right? So you will be using, if you're using a right angle, um, 90-degree triangle rule, so half times the base times the height. So your total distance covered in this case would be just multiplying all of these together. So 0.5 times 0.08 times 30. Um, that's going to be 1.2 miles. However, if you move back to the actual case, you've covered 2.5 miles. So this doesn't add up. So that means that this graph, that if you were to point it out, plot it out based on that data, this is incorrect. So there's a big cross right here. So don't use this one. What you have to do then is you have to actually go back and modify your data. And this is something what your journey would look like if your car was able to accelerate instantaneously. So it was, you press on the accelerator and it goes from 0 to 30 instantaneously. So that's what this is telling you. But essentially what you're trying to do is at time 0, you were at 0, your speed was 0, and then at time 0, so that's what I mean by instantaneously. So there's no lapse in time for you to reach that speed. Then again, at time 0, you're at 30 miles per hour, then 0.08, you're staying at 30 miles per hour, where you then accelerate, hit the pedal, you reach 67.38 miles per hour, stay constant for a certain amount of time, where you drop your speed to 42.26, and then increase it and stay constant for that speed for another 0.38 of an hour. Uh, then increase, accelerate to and reach 64.13, and so on and so forth, right? So that's one thing you can do. Uh, so here's one more question before we move on further: displacement and velocity. So if I were to drive from to Sisters of Notre Dame campus from CJ and then drive back, what is my total displacement going to be, and what will be my velocity for each side and for the total journey? That's something you'll have space on your end class assignment for you to fill out. Right. So moving on. Um, More realistically, what your journey would look like is that you'll start at 0, And this is what your initial magnitude of velocity is going to be, and I've added directions now. What you will be doing is you'll start at zero. After some time, you'll reach your um, velocity or speed limit for that road that you were on. Uh, and then after some time, you will then decide to increase your speed. You'll reach that speed after a certain time has passed right here. Then you'll stay constant on that speed. You'll keep moving and so on and so forth. So remember, I'm using the same sort of speeds from our previous example, but we're applying and we're trying to calculate acceleration at this point. Um, so this is how the time is progressing, and this is how your velocity journey is looking now. So this is something that you did for your, I believe, your very first in-class assignment, or for visual techniques assignment, actually, the first question of visual. So this is something that I was kind of looking for. Yours might differ because you were stopping and going and that sort of thing, so that could be different. But essentially, this is the graph that I was looking for, right? And notice I'm labeling the axis here. I've got velocity magnitude labeled here because I cannot insert the directions or so. And then I've got time, and then I've got the units here, so I don't have to write R's against each one of these. Again, Google Sheets does not like having extra information in here. You can have letters and both numeric digits, both of those here, and Google Sheets will not have a problem. If you try to do that on your y-axis, it will not add the data to your graph or any chart that you're trying to add to. Anyways, continuing from where I was talking, so I've got these, and this is a bit more realistic, where it's not an instantaneous change, but it's a relatively speaking, a gradual change in your velocity. There's a slight increase in time before you reach your speed limits for the different sections of the route that you took. Right, so that's what's happening. Now, if I were to get to measure acceleration, let's focus on one part of the journey where I've noted down these points, and these points are again from the table on the previous slide, where I accelerated from a velocity of 30 miles per hour at zero point zero 0.08 hours. And at zero point zero 0.09 hours, my velocity had reached 67.38. Now, going back to the acceleration formula, which is change in velocity over change in time, this is what my acceleration looks like by just plugging in the numbers. Um, if I were to move on to the next slide, and then if I were to note this leg of the journey, what I've got here is my velocity is changing, but I'm reducing speed, right, as the time increases. So what happens is that I've got a negative acceleration of 341.3 miles per hour. So remember, I had asked you what is the acceleration and what is the deceleration in the last assignment that you did. Um, well, acceleration is negative 341.3 for this little part right here, whereas my deceleration is going to be simply, I remove the negative sign. It's just another way to use that word. I haven't looked at your answers, but I just wanted to clarify that in case you were wondering what I meant by deceleration. So that was a little trick question, but it was a very easy trick question, per se. Um, so that's how you calculate acceleration or deceleration for different legs of the journey. And you're using the velocity time graph to calculate these, but you're only calculating it for where there's an actual increase. If you were to try to compute or calculate what the acceleration is for this leg of the journey right here, where the speed does not change, you will get an acceleration of 0 miles per hour square. And that's the end of the lecture. What I would like you to do is answer the question that I had asked you in the presentation. And there are some more questions regarding speed and position and velocity and acceleration that I would like you to answer and the remainder of the time and submit those to me once you're by 5 p.m. today. Again, thank you for your attention. Have a good day and bye bye.